My name is Geng Li. I'm from Huawei Canada. I'm currently the manager of Huawei Canada Network and Protocol team. So it's my pleasure to introduce our work, Panorama, optimizing internet-scale users' routes from end to end. So recent years, the number of real-time communication or real-time interactive application and their users increases exponentially. For example, the video conferencing product have increased like 30 or 40 times since COVID-19. And also the online gaming, VR, AR, and live streaming become more and more popular. However, driven by the continuous improvement in interactivity and video quality, the emerging applications impose much more stringent requirements in network performance, such as latency, throughput, or packet loss. So we can see empirical studies show that transparent latency over 300 milliseconds would become unacceptable for video streaming. And actually the cloud gaming and VR and AR have more stringent requirements. Unfortunately, internet, which was originally designed for connectivity as a best effort infrastructure, can hardly satisfy such strict performance requirements because, as we all know, the internet is connected by BGP and the route basically is selected by the commercial relationship instead of performance. So the internet path is not optimal to provide a good performance to these real-time applications. To address that, in the past few decades, a lot of efforts have been made in designing and building the overlay networks for the purpose of overcoming the internet's inherent inefficiency and other limitations. We can see an overlay network is like a logic network built on top of the underlay or the physical network or the public internet. So it is first designed to improve fault tolerance like recovery and reliability, and then studied to provide better service performance recently. And basically, instead of using the default internet path, an overlay path can provide better performance. So an overlay network consists of a number of distributed overlay nodes. Here we call service edge. And each service edge placed as an relay node that can receive and forward packet to the user or any other SE. Here, the connectivity can be hybrid, including both private link and internet link. Actually, in our deployment, it is indeed hybrid deployment. And we found that actually public internet overlay is a very important addition to even the private network. Okay, because building this large-scale private network is very costly. Unlike other companies like Google, they have the big backbone network. Actually, our strategy is to build this hybrid connectivity for the real-time backbone network. So the private link actually are used on critical overlinks in a like circle star-like topology. That's in the figure. And the internet links connect every two SEs in a full mesh manner. And also between two SE, actually the private link and public can coexist. And we just implement this by installing two different NIC cards in the forwarder or the SE. And we found the public internet is a good addition, and in terms of providing good, capacity and also offloading traffic. And we believe it's not just some preliminary strategy for low-cost networking, but can be also trained for building large-scale ones in the future. So on top of the overlay network, many overlay routing schemes are proposed. And our previous solution, or like our traditional solution, is we call the nearby access and backbone optimization. By saying that, I mean the nearby access is for each user actually is associated to the closest SE in terms of distance or latency. For example, in this figure, the user A will get associated with SE1, and user B will associate with like SE5, and they will find the shortest path in the backbone. And for backbone shortest path, right now previously our approach based on latency. Basically, we periodically collect latency of every overlay link and use just very simple shortest path first algorithm to compute the optimal path between any two SEs. Or like in other backbone or related work, they have more sophisticated traffic engineering or routing method. So we can find one issue here. Basically, in this approach, we can find the path like from user A to SE1 to SE2 to SE4 and SE5, then user B. But this approach cannot find other alternative paths like from user A to SE1 and then SE3 that directly to user B, or just use SE3 as the single hop. So actually, this approach was widely used in existing accelerating network system like AWS and Google Premier like network service, with the condition that the backbone performance or the quality is much better than the public internet. However, in our hybrid deployment, we do find many issues. And all these issues will be illustrated with real concrete examples. So first, it will lead to suboptimal in the end-to-end aspect because the access and backbone network are optimized individually instead of jointly. Here we have the example, the user from Argentina and the other one from Portugal. And the previous method path will get associated to the Argentina SE and to Brazil. And for the Portugal user will associate to Dubai. Okay? And the whole latency of this path will around 260 milliseconds. However, we have a better path. If the Argentina user can connect to a slightly further SE, like to Brazil, and also the Portugal, instead of choosing the closest SE, but choose a further one, like the Brazil, the whole end-to-end latency will become 140. And second, it will lead to degradation in other performance metrics because a low latency path may suffer from a large packet loss or jitter. Here's an example from the UAE user, okay, to the Hong Kong. If the best or the lowest latency path will have a very high jitter in the link from Dubai to India, but we can choose a second lowest latency path, but with very low jitter. And third, it will missing the trade-off between performance and cost. Sometimes a huge cost path with tiny and even you cannot perceptible kind of improvement here is unnecessary. In this example, we can see from Argentina to Thailand, the lowest latency will have 5 hops, and leading to like large cost. But we can choose a slightly slower path, but also with similar kind of latency, but only 2 hops. And also with issue like a balance load among SE and so on. So all these issues are pervasively existing instead of just some real engineering practical problems. So we need a better design. Therefore, we propose this Panorama, a scalable system for delivering desired user experience to real-time applications over the overlay network. And the challenges were addressed at these 3. First is the tight SLA requirement. Basically, you need to consider all these metrics like latency, like jitter, and also throughput will be our next step to consider. And also, because the communication is worldwide, you need to do the end-to-end optimization, joint optimize the the routing and connection in the access and also the backbone network. And also handling internet with millions of daily active users itself is a difficulty. So here's our system. We can see this figure. So Panorama runs a logically centralized control plane to compute and manage the overlay routing for all communication sessions. And also we deployed numbers of route servers to offload routing queries from millions of users to global controller, also to bring the routes request service closer to users. And for the ICE and the user, we develop hands-on SDK for application developer to use Panorama and the overlay network service in a very simple way. The user SDK actually support a variety of applications from the client, we support from the mobile and the computer, and also we support some backend server like the web servers, CDN, SFU, or HTTP servers. So about the API, actually we have two sets of API. One is initialization to download some information, and also the sending data API. Here is very simple. The application will create just a local socket FD, and then will call this function to send data using Panorama. And for the workflow, the user will first request route from the route server, and from some lookup, it will return the path, and the data will be forwarded using source routing with this kind of encapsulation. So scalability will be the major challenge to handle all the user. Therefore, we need this user and session grouping. Ideally, the sessions in the same session group can share the same best routing decision. Of course, the session group will depend on the user group. It's just like user group pair. And for previous nearby access routing, the user grouping can be very simple. Just the lowest latency SE. So in this figure, we'll have like 4 groups. But for the end-to-end based routing, actually, the grouping can be much more complicated. And we can see you have more user group scale, a large user group scale, and also difficult to determine. In this example, it would become like 8 user groups. So our solution is very simple. We first have the minimal granularity of UG as the IP prefix like /24, and then we combine all the we just do some measurement. We rank all the SE in the ascending order of latency. Then we combine all the /24 blocks into user group that have the same SE in the top 2. Here we have 2 positions. And the details can be found in the paper, but it turns out like from the 750K active IP blocks, we will only need 3K user group, and with around 30 SEs. And then we have this overlay routing and the traffic engineering block. So we have 3 phases. The first phase, based on the overlay network topology and real network measurement, will have the top K shortest path calculated. And then we use a scalable and heuristic manner. So phase 2, and we exclude the path that cannot meet the SLA requirement for each survey class. And for number 3, phase 3, considering both traffic cost and link utilization, a simplified MCF multi-community flow problem is solved to compute the path weight for each feasible path set. And by default, the controller will run this every 5 minutes. So first is about heuristic KSP. Okay, the problem is to compute the K shortest path for each SG or the UG pair. And the major challenge is scalability. If we consider millions of UGs as a node, basically it's computational infeasible. So our solution is try to reuse the backbone KSP to compute every UG pair. Here we have the one big switch abstraction, and because the idea is UG cannot use another UG as a relay node, it will only choose the SE as the ingress or egress node. Then based on this abstraction and with a KSP in the backbone, the UG can just simply choose or search the ingress and egress, and then of course add the latency of the access segment, and then compare the entire latency. And our method is the searching method has some optimization based on reinforcement learning. Here we don't give the details. As a result, we can see actually the time actually become much more faster. Even we consider 1 million SG, the time is even less than 1 minute to compute the KSP. So the above KSP is computed solely on latency, but sometimes a low latency may suffer from large packet loss or jitter. Therefore, we have the SLA filter here. Okay, so the SLA requirement is defined as 3 upper bound thresholds of latency, jitter, and loss. The table shows the SLA requirement used currently, and we have the diversity in the service class to balance the performance and the price for user. And basically, we have a very simple algorithm. The principal algorithm is to try to find paths to satisfy all SLA threshold. If not, try to find the best performance one with some reduction. Again, we don't give the details here. So the real network performance of paths may not be consistent with the estimated performance because of the congestion. That's why we need the phase 3 to weight allocation in the feasible path set. And because we want to minimize congestion, so the objective is to balance load and minimize what we call the cost-weighted maximum link utilization. And here we formulate into a simple multi-commodity flow problem and solve it with some optimization. The details can be found in the paper. About evaluation, we use 81 million session instances in the real deployment environment. And here the ICE we consider like 30 plus locations. And for users, we consider users from 66 countries. So for the improvement on some general network metrics, we can see for both latency, loss rate, and jitter, the Panorama has all this gain. For example, for the 50, 90, and 99%, we have around the 10%, 17%, and 23% over nearby method, and also with some improvement over the direct internet. And one may notice there's some negative gain and compare with both the direct, especially from the direct internet. So indeed, for some short distance sessions, there's no need to use this overlay network, which will incur extra latency and jitter. However, most of the negative gain will not be perceived by user because they happen only in the session less than 100 milliseconds. So therefore, actually the negative gain will not affect the user experience. The main benefit of Panorama is not to turn a good quality session into a great quality session, but to change a bad quality session into good quality ones, because the latter one can truly improve the user experience to meet the SLA requirement. So from our result, we can see we reduces the over 300 millisecond sessions by around 97% than the nearby, and 99% than direct. And also, we have the experience latency of around 96% sessions can be limited under 200 milliseconds. And almost all the sessions can be limited under 3 milliseconds. And also bad quality sessions with large loss and jitters can also be reduced. So to conclude, Panorama basically pushes the software-defined domain to every end user and optimize routing from end to end. And it systematically addresses the scalability challenges in multiple dimensions with coherent combination. And the Panorama has been proved to perform well in real-world environment. So while our approach does not be general to all wide area network, but we hope that our experience summarized from our practice with real system can inform future work in this domain. Thank you very much. I'm happy to take any questions.